There are many types of gears with slightly different gear mesh configurations. Spur, helical, and bevel are just a few examples. In this video, we're going to go over some of the essential criteria for spur gear design, the various characteristics of the tooth profile, and later in the series, how to draw the profile. To start, we can split each tooth into 4 faces. The top of the tooth is the topland, while the base of the tooth is the bottomland. When 2 gears mesh, these faces never meet. The top face of one gear will always be in clearance to the bottom face of the other. The sides of the tooth are split into face and flank. The dividing feature is the pitch circle, which will be explained in the following slides. The 2 gears shown on screen have vastly different diameters. If the smaller gear is the driver, for example, the size increase will cause a decrease in the revolutions per minute or RPM achieved by the larger gear. This is called gear ratio. We're not going to cover this in this video in great detail, but it is useful to illustrate gears of different sizes, as no matter how big one is compared to the other, they must share certain characteristics in order to guarantee the two will mesh. So let's overlay some parameters. The pitch circle or diameter of each gear links the two, and the difference in diameters of these circles dictates the ratio of the gearing. The gears on screen have a ratio of 2:1. The smaller gear rotates 360 degrees twice for every single rotation of the larger gear. The pitch circle is generally one of the first parameters a gear mechanism designer will need to decide upon. However, it can be calculated by multiplying the module by the number of gear teeth. The addendum or module is the distance between the pitch circle and addendum circle diameters. The addendums must be identical for all gears meshing, as different addendums will have differing tooth depths and spacing. This inconsistency could cause misalignment and lead to the mechanism seizing up. The module can be calculated by dividing the circular pitch by pi. For argument's sake, all circles discussed here are calculated as diameters. With this in mind, the addendum circle can be found by adding the pitch circle to 2 times addendum or modules. The root circle forms the diameter of the tooth bottom face. This and exists in clearance from the addendum circle and corresponding top face of the meshing gear. The calculation is pitch circle minus 2 times the addendum, which leads us to the addendum. This is another parameter that is constant across all meshing gears. The addendum is generally 1.25 times the module, and as the offset is greater than that of the addendum, assists tooth clearance. The whole depth of the tooth profile, or height, is therefore module plus addendum. So the clearance circle should now be a formality. It must be larger than the root circle, and it intersects with the addendum circle of the meshing gear. The pitch circle is found by deducting 2 times the module. The circular pitch is the length of the arc from any given face or point of one tooth along the pitch circle to the corresponding face or point of the next tooth. It is essential for calculating the module and vice versa, and the calculation is module times pi. The base circle is one parameter that can be vastly different across both meshing gears. In the case of this gear scenario, the larger base circle is close to the clearance circle, while the small gear base circle is nearer the pitch circle. The calculation for the base circle is pitch circle times cosine of the angle of the tooth interaction. The angle of interaction, line of action, or pressure angle is the angle of the line between the two base circles, connected by tangents. The line and angle refers to the direction of the force through the tooth contact. The larger the pressure angle, the smaller the base circle diameter. This feels like a good point to pause the tutorial. In the next video, I'll look at the involute gear tooth profile, how to calculate the arc, and which circle to offset it from.